All right, take a good look at this thing on your screen. I mean, really look at it. It's an 18th degree polynomial. It is a mathematical monster, just packed with terms and, well, complexity. Now, if you're looking at this and your first thought is, where would I even begin? You are definitely not alone. Honestly, it looks flat out impossible to solve.
But what if it's not impossible? What if there's a brand new key that can unlock problems just like this one? That's what we're doing today. We're going to dive into a pretty fascinating breakthrough that takes on this ancient mathematical challenge and does it head on.
Okay, first things first, let's just take a moment to really appreciate the scale of what we're up against here. Because this isn't just some random string of numbers. No, this is a challenge with a very, very long history.
You know, for hundreds of years, some of the greatest minds in mathematics have been wrestling with finding the exact roots of these complex equations. In fact, there's a famous theorem by Niels Henrik Abel that proved there is no general formula using simple things like square roots or cube roots to solve any polynomial of degree 5 or higher. Basically, they were stamped as unsolvable in any neat, tidy way.
And remember, we're not just dealing with degree 5. We're talking about degree 18. That means there are 18 different solutions, 18 roots hidden somewhere inside that massive equation. And finding every single one of them exactly, well, that is a truly monumental task.
So if you can't solve it directly, how did people even try to tackle this in the past? Well, you get close enough. But as you can imagine, close enough comes with its own big set of problems.
On one side, you've got the classical methods. You can think of these as, well, educated guesswork. They use numerical approximations to slowly, carefully inch closer and closer to the right answer. But they're always haunted by these tiny rounding errors, and they can never ever promise you a perfect exact value. But on the other side, we have this new method, built on Ezouidi's theorem, and it promises something totally different, a guarantee of the exact symbolic roots. It just completely bypasses those old school limits. And that right there is the whole problem. Approximations are incredibly useful for sure, but they aren't the truth. They're just a shadow of the real answer. And for pure mathematics, that distinction means everything. Which, of course, raises the big question, how in the world do we get to that real answer?
And this is where the hero of our story walks in. Let's talk about Ezouidi's theorem. This is the new tool that promises to finally slay that mathematical monster we saw earlier.
So, what's the secret sauce here? What makes this theorem so powerful? It's all about the process. It's not about guessing, it's a systematic, step-by-step procedure. The magic word, remember, is recursive. It just means that each step in the calculation literally feeds the next one, building on itself until the final exact answer pops out. No guesswork, no rounding errors. Period.
Think of it like a super complex but super precise baking recipe. You don't just dump all the ingredients into a bowl at once, right? No, you perform one step, you see the result, and that result tells you exactly what to do next. It's a guided process, and if you follow that recipe perfectly, you're going to get a perfect result every single time.
Okay, the theory is fantastic, but let's actually see this thing in action. It's time to apply the recipe to our degree 18 monster and see what secrets it's hiding. The game plan really boils down to 3 steps. First, we apply the theorem's special recursive formula. This lets us calculate a whole new set of 18 values, these symbolic coefficients that we'll just call S. You can think of these S values as a kind of secret key. Once we have them all, they are going to reveal the hidden and much simpler structure of the original problem.
Okay, here we go. We start the process. The first coefficient, S0, gets calculated, and the result is 0. Okay, interesting.
So then we calculate the next one, S1, and the next, and the next. A really strange pattern starts to emerge. From S1 all the way up to S7, they are all 0. The theorem just seems to be simplifying things a lot. What is going on here?
And then, bam, we get to step 8, and the pattern shatters. The coefficient 8 is not 0, not even close. It's this enormous number. This is a huge discovery. It's like the first structural pillar of the solution that the theorem has managed to uncover for us.
But then, just as suddenly as that excitement appeared, we continue the calculations from S9 all the way to S16, and we're right back to 0, all of them. And that just makes that one non-zero result we found for S8 even more important. So let's just step back and look at what we found. We ran 18 of these recursive calculations to find our S coefficients.
And here are the results, all laid out. Out of 18 total coefficients, almost all of them just vanished into zero. Only 2 actually had a value, S8, and the very last one, S17. It's like the theorem just filtered out all the noise and pinpointed the only 2 parts of the entire equation that actually matter. And folks, that discovery changes everything. We are now at the final stage, where all that insane complexity we started with is about to collapse into something, well, something beautifully simple.
Remember this guy? The sprawling, intimidating absolute unit of an equation we started with? It looked like a completely unsolvable mess. And now, look at what it becomes. Because all those S coefficients were zero, their matching terms in the new structure just poof, they vanish. We're left with just 3 terms. The monster has been completely tamed. This is now basically a simple quadratic equation, it's just in terms of x to the power of 9. And from that much simpler equation, we can derive the final roots exactly. This right here. This is the trophy at the end of the battle. The solution isn't some fuzzy approximation, it's a formula to find all 18 roots with perfect mathematical precision. We've bypassed the old limits entirely. And this is the ultimate takeaway. Let's be crystal clear about this. What we've found isn't an estimate. It's not a close enough value. It is the exact, precise, mathematically guaranteed solution, derived through pure logic. It's the difference between seeing a fuzzy shadow on the wall and finally turning around and seeing the actual object that was casting it. This whole process really makes you wonder, doesn't it? It just goes to show how a problem that seemed completely unsolvable for centuries could be cracked wide open by just a new way of thinking. And it begs the question, what other impossible challenges that we face today, whether it's in math or anywhere else, are just waiting for that one new theorem, that one new perspective to transform them from impossible to solved?